For decades, nuclear power was hailed as the future of energy, clean, efficient, and virtually limitless. Its complex systems, safeguarded by layers of redundancy, were designed to withstand the unimaginable. Yet, on March 28, 1979, the promise of this powerful technology would be profoundly shaken. At the 3 Mile Island Nuclear Generating Station near Middletown, Pennsylvania, a series of seemingly minor malfunctions began an escalating chain of events, pushing a pressurized water reactor to the brink. This was not a catastrophic explosion, but a slow, agonizing unraveling, a testament to how the smallest flaw can cascade into crisis. 3 Mile Island Unit 2, or TMI-2, was a modern pressurized water reactor, a design considered inherently safe. In a PWR, water is heated by the nuclear core but kept under immense pressure to prevent boiling. This superheated water then transfers its energy to a secondary loop, producing steam to drive turbines. Safety systems were integrated at every stage, from control rods designed to shut down the fission reaction, to robust containment structures. The sheer complexity of these systems, however, also introduced vulnerabilities, particularly at the interface where human operators interacted with the machine's intricate signals. The crisis began, innocuously enough, in the non-nuclear part of the plant. A blockage in a condensate polisher, a filter system for the secondary loop, prevented water from reaching the steam generators. This caused the main feedwater pumps to trip, leading to a turbine trip and, subsequently, an automatic shutdown, or scram, of the reactor. This sequence was a common occurrence, a routine safety response designed to manage minor disturbances. Operators were well trained for such events, expecting the plant to stabilize as auxiliary systems took over. But this time, something fundamental would fail to perform as expected. When the reactor scrammed, the sudden cessation of fission heat caused an immediate pressure surge in the primary cooling system. To prevent overpressurization, which could damage pipes or the reactor vessel, a safety device known as a pilot-operated relief valve, or PRV, on the pressurizer automatically lifted. Its function was to vent excess steam and water from the primary system into a drain tank, thereby reducing pressure to safe levels. Once the pressure stabilized, the PRV was designed to reseat, closing off the vent. It was a critical component, a safety measure intended to protect the system. Here lay the crux of the crisis. While the PRV had indeed opened as designed during the pressure surge, it then failed to reseat. A small indicator light in the control room, however, only signaled that the solenoid valve, which controlled the PRV, had been de-energized, not whether the PRV itself had physically closed. This crucial distinction created a perilous blind spot. Operators believed the PRV had closed, as it should have, based on the indirect signal. But, unknowingly, the valve remained open, creating an uncontrolled, continuous leak from the primary system. This unseen outflow was now rapidly depleting the reactor's vital coolant. With the PRV stuck open, the primary cooling system began to slowly bleed off its coolant directly into the reactor's containment building. This was a loss of coolant incident, a grave scenario that could lead to the reactor core overheating. As coolant escaped, the pressure in the primary system plummeted. In response, the Emergency Core Cooling System, or ECCS, automatically activated, injecting borate water into the reactor vessel. This was precisely what it was designed to do: prevent the core from becoming uncovered. But the operators, relying on their flawed understanding of the situation, were about to make a series of critical, compounding errors. The control room at TMI-2 was a vast, sprawling console filled with hundreds of gauges, lights, and alarms. In a crisis, operators were expected to synthesize this deluge of information, often under immense pressure. The problem was not a lack of data, but a lack of clarity, a poor human-machine interface. Critical indicators were scattered, difficult to interpret, and often presented conflicting information. It was like trying to navigate a ship through a storm using a map where some of the crucial markings were either missing, obscured, or outright misleading. The true state of the reactor was obscured by a fog of fragmented data. A critical piece of misleading instrumentation was the pressurizer level indicator. The pressurizer's role is to maintain pressure in the primary cooling system and provide a steam bubble to absorb volume changes. During the accident, as primary coolant escaped through the stuck-open PORV, pressure dropped, and the water in the reactor began to flash to steam. This created a large steam bubble inside the reactor vessel, driving water into the pressurizer. The pressurizer level indicator, therefore, showed a high or even full condition. To the operators, this indicated that the primary system contained too much water, signaling a threat of water hammer if ECCS continued. Confronted with the high pressurizer level, and believing the system was overfilling, the operators took a drastic action. They throttled back and eventually shut off the emergency core cooling system pumps. This decision, based on a misinterpretation of a single, highly misleading instrument, was catastrophic. The ECCS was the last line of defense against core damage, actively pumping coolant into a system that was, in reality, rapidly losing water. Instead of adding vital cooling, the operators were unwittingly starving the reactor core, transforming a manageable incident into a full-blown emergency with potentially dire consequences. With the PORV still open and the ECCS throttled, the inevitable began to unfold. The water level in the reactor vessel continued to drop, uncovering the upper portions of the nuclear fuel rods. Without the cooling effect of the water, the fuel rods began to rapidly overheat. This extreme heat caused the zirconium cladding surrounding the uranium fuel pellets to react with the remaining steam, producing hydrogen gas. This gas, highly explosive, accumulated within the primary system, adding another layer of danger to an already perilous situation. The core was literally boiling itself dry, exposing the very heart of the reactor. Within hours of the initial incident, the lack of cooling led to severe damage to the reactor core. Fuel rod cladding began to rupture, releasing radioactive fission products into the primary coolant. Portions of the uranium fuel pellets themselves melted, leading to a partial meltdown. This was the dreaded core damage scenario, though thankfully not a complete meltdown of the entire core. The release of radioactivity, primarily noble gases, into the containment building, and subsequently into the atmosphere through filtered vents, caused significant public alarm and necessitated a partial evacuation of the surrounding area. The integrity of the reactor was compromised. 3 Mile Island exposed profound flaws in the human-machine interface. The design of the control room instrumentation failed to effectively communicate the true state of the reactor to its operators. Key information was either absent, like a direct indicator for the PORV's physical position, or presented in a way that was easily misinterpreted, such as the pressurizer level reading. This created an excessive cognitive load on the operators during a high-stress event, making it almost impossible to correctly diagnose the unfolding crisis. It wasn't just about operator error, it was about a system that was designed to be unforgiving of human fallibility. It took several agonizing hours, and the arrival of highly experienced engineers, to fully comprehend the true nature of the problem. The critical breakthrough came when an engineer realized that the auxiliary building's temperature and radiation monitors indicated a continuous discharge from the PORV's relief line, confirming it was still open. Only then could the operators take corrective action, manually closing a block valve behind the stuck-open PORV to stop the leak. This delayed diagnosis underscored the systemic failure of the human-machine interaction and the insufficient training provided to operators for such complex, beyond-design basis accidents. Once the leak was stopped and the true situation understood, the immediate priority shifted to cooling the damaged core and bringing the reactor to a safe, cold shutdown. This was a painstaking, weeks-long process. Crews had to deal with the residual heat generated by the damaged fuel, the accumulated hydrogen bubble in the reactor vessel, and the constant threat of further radioactive releases. It was a battle against unseen forces, requiring innovative engineering solutions and immense bravery from the recovery teams. The world watched, holding its breath, as engineers and operators worked tirelessly to avert an even greater disaster. In the wake of 3 Mile Island, President Jimmy Carter appointed the Kemeny Commission to investigate the accident. Its findings were stark and uncompromising. The report concluded that no single mechanical failure was solely responsible, but rather a combination of equipment malfunctions, design deficiencies, and, crucially, inadequate operator training and human error. The Commission pointed directly to the misleading instrumentation, the lack of clear procedures, and a safety culture that had become complacent. This comprehensive review provided the critical foundation for transforming nuclear safety protocols globally, emphasizing human factors as much as engineering integrity. 3 Mile Island became a watershed moment for the nuclear industry worldwide. Nations reviewed their own nuclear programs, leading to unprecedented changes in safety philosophy and operational practices. The emphasis shifted dramatically from purely technical fixes to a holistic approach that included rigorous operator training, often utilizing sophisticated simulators that could replicate every conceivable accident scenario. Control rooms were redesigned for clarity, with improved display logic and direct indicators for critical safety components like the PORV. The lessons learned here resonated across every nuclear plant on the planet. The accident prompted a fundamental re-evaluation of reactor design, particularly concerning the human-machine interface. Engineers implemented numerous upgrades, ensuring that safety-critical information was presented clearly, unambiguously, and in an integrated fashion. Direct position indicators for valves like the PORV became mandatory, eliminating the guesswork that plagued TMI operators. Alarm systems were rationalized to prevent nuisance alarms from obscuring real threats. The goal was to create more forgiving designs, where potential operator errors could be better mitigated or even prevented by clearer, more intuitive system feedback. This was a move towards safety through intelligent design. The legacy of 3 Mile Island is complex, but ultimately, it ushered in a new era of nuclear safety. It forced the industry to confront its vulnerabilities, moving beyond a sole reliance on robust engineering to embrace the equally critical role of human factors, training, and a proactive safety culture. While the accident effectively halted the expansion of nuclear power in the United States for decades, it paradoxically made existing and future plants significantly safer globally. The event underscored a profound truth: even in the most technologically advanced systems, the human element remains the most vital, and often the most vulnerable, link.